Hello class, today we're going to talk about functions, which is part of section 1.1 part 1. Our objectives are going to be to decide whether relations between two variables are functions, to use function notation and elevate functions, and to find the domains of functions. Okay, so just an introduction. Pairs of quantities that are related to each other by some rule of correspondence is called a relation. For example, there's a relation between area and radius, and the formula a equals pi r squared, which is the area of a circle. And there's a relation between starting quarterbacks and touchdown passes. So when a relation matches each item from one set with exactly one item from a different set, it's called a function. And that's what this section is going to focus on. A little more information. A function f from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. The set A is the domain, which is the independent variable or the input of the function, and the set B contains the range, which is the dependent variable or the output. And typically when I talk about domain and range, I like to say, and when we try to figure out which one is the domain, I say, well, does this depend on this or does the other depend on it? For example, would time depend on number of people, or does the number of people depend on time? So those are different things that we'll use to talk about domain and range. So in example 1, it says decide whether the description represents y as a function of x. So the input value x is the number of representatives from a state, and the output value y is the number of senators. First of all, we have to know a little bit of context. As far as representatives for each state, the amount of representatives that are assigned to each state are based on basically proportional to the size of that state. So, for example, Alabama may have 7, Alaska may have 1, Arizona may have 9, just examples. But the number of U.S. senators per state is 2, no matter what. So if we were to chart that, didn't mean to move the whole thing. If we were to chart that, we'd have our X and our Y. All of our X's might, for the most part, be different. So we may have, like I mentioned, 7 for Alabama, 1 for Alaska, 9 for Arizona, and 4 for Arkansas, just to throw another number in there. But all of the senators are 2. Okay. With that being said, this is a function. I like to describe it as what's faithful, what's not faithful. So I typically say that X is the female and Y is the male. And in society, for some reason, it's not okay for females to talk to more than one person, but it's totally fine for guys to talk to more than one person. So each female is actually very faithful in this situation because, for example, 7 only goes to 2, 1 only goes to 2, 9 only goes to 2, and 4 only goes to 2. So in this case, this is considered a function. An example of what would not be a function is if there was another state that had 4 representatives and it also obviously went to 2. That would make this whole thing not a function. So we're just going to assume that all of the states, because they all have different population sizes, that they all have different amount of representatives. Let me erase some of this information so that we can talk about the next set. All right. The example 2 says, well, actually it's turned sideways. So I'm going to do something really interesting. I'm going to turn this graph. Sorry, it was supposed to look like that. So on this example, we have, remember I mentioned that your x must only go to one value. And another way for us to test functionality is to use the vertical line test, and that's going to come up in just a moment. But either way, if I focus on my x values, for example, here, -2 only goes to 3. Here, -1 only goes to 0. Here, 0 as its x value only goes to -1. Here, the value 1 only goes to 0. And here, the value 2 only goes to 3. So in this case, this is also a function because each x value goes to exactly one y value. So yes, a function. All right, let's keep going. So in this try, it says to decide whether the description represents y as a function of x. In this example, this is actually not a function simply because we have two inputs that are going to different outputs. Remember, I mentioned it's more so about if the female is faithful. So is x faithful? Is it going to the same number? If it is, then it is a function. If it's not, then it's unfaithful and it's not a function. And in this case, 2 goes to not only 11, but it goes to 10. So this is not a function. In example 2, it says, does the equation represent y as a function of x? So here we need to manipulate the equation so that we can isolate y so that we can see what type of function that it is. And then after we've decided that, either, if you know what it looks like graphically or graph it on a graphing calculator, you'll get an opportunity to see what it will do then. So for us, what we're going to do first is we're going to isolate y. So we need to subtract x squared on both sides. We're left with y equal to -x squared plus 1. So since it's left with y equals -x squared plus 1, if you remember from Algebra 2, this is a parabola that opens downward but has been shifted up 1. So just as a sketch, it's a parabola that opens downward and has been shifted up 1. If we were to do a vertical line test, and again, I know I keep mentioning this, it's going to come up later, but if we were to apply a vertical line test, and imagine that this line is actually going and shifting and moving in this direction, right? This vertical line will never be touched in more than one place at one time. So for example, while it's here, it's only touched once. While it's here, it's only touched once. So this function will actually pass the vertical line test. So again, this is a function. Here in this example, again, we'll need to go ahead and isolate y. So here we go. We need to add x to both sides. We're left with y squared equal to x plus 1. And then we need to get y by itself, so take the square root. You have to be careful on this one because a lot of people will make the mistake and say that y is equal to the square root of x plus 1. But that's only half of the answer. Remember, when you take the square root, there are technically two sets of solutions. It's the positive set of solutions and the negative set. So technically it's plus or minus the square root of x plus 1. Now, radical functions, again, just a refresher from Algebra 2. Radical functions tend to do a graph that I call like the liftoff. And because it's plus 1 under the radicand, it has been shifted to the left 1. So the positive version would lift off this way, which, yes, in that case, it would pass the vertical line test. However, the negative square root of x plus 1 version of that function would go under. So in that case, it does not pass the vertical line test because it's going to hit the vertical line in two different places. So no, this one is not a function. This is just getting you familiar with function notation. Function notation is used as a convenience to name an equation known to be a function. So if you see f of x, they're telling you that it is a function. If you see just simply y, we would probably need to test it using what we just did to see if it is a function or not. But it's just a sort of notation, that's all. All right, so now we're going to start evaluating functions. This may feel a lot more familiar, especially like if you think back to your Algebra 1 days. This simply just means that we're going to substitute. So for this first example, we are substituting 2 in the place of x in our function. So here we go. We would have negative 2 squared plus 4 times 2 plus 1. If we know and are reminded of our order of operations, in this case right here, you have to remember that exponents comes before multiplication. So in that case, we would say 2 squared first, which is 4, and then we would multiply that 4 by negative 1, which makes this negative 4. All right, if we proceed, we have negative 4 and then plus 8 and then plus 1 at the end. In the end, our answer is 5. So g of 2 equals 5. On to the next one. We will substitute now t in for x. So in this case, it's really more so, it's going to look the exact same as a g of x, just replaced with t. So g of t is negative t squared plus 4t plus 1. And that's it. Let's keep going. Here we are substituting an expression, x plus 2, in for our x. So again, we are substituting the entire expression. So that will look like g of x plus 2 equals negative x plus 2 squared plus 4 times x plus 2 and then plus 1. And this situation here, please do not distribute the 2 inside or just say, oh, it's x squared plus 4. That's not how that works. Essentially what you need to do is you need to expand it. So in other words, this is really negative x plus 2 times x plus 2. We'll just work on this first. Using the distributive property, or some of you like to call it FOIL, but really it's the distributive property. If you multiply the firsts, remember this negative is on the outside, you'll have x times x, which is x squared. Your outsides would be x times 2, which is 2x. Your insides is 2 times x, which is 2x. And the last terms are 2 times 2, which gives you 4. Let's go ahead and combine before we throw anything else down here. So we'll have negative times x squared. Your two x's are the same. So that becomes 4x because 2x plus 2x equals 4x, and then plus 4. Let's continue to add everything else down here. So let's distribute now. So if I distribute the negative to everything inside, this will be negative x squared minus 4x minus 4. Again, if we continue to go from where we had at the beginning, we need to distribute that 4 now. So 4 times x is positive 4x. 4 times 2 is positive 8. And then finally, we just drop down that positive 1 at the end, so plus 1. Now, when we combine all of our like terms, we have negative x squared. The other like terms that we have are the x's, but in this case, negative 4x and positive 4x will cancel one another. And then we're left with our whole numbers, negative 4, positive 8, and positive 1. That will leave us with positive 5 as our final answer. So g of x plus 2 equals negative x squared plus 5. Okay, piecewise functions. And we'll talk more about piecewise functions, but for now, we're just going to practice evaluating them. The thing that you need to understand, and I'm just going to give you kind of like a rough sketch. A piecewise function, they are pieces of functions. So for example, I may have a function that is constant in one part. Sorry, I meant to do it like that. Constant in one section. And then out of nowhere, it may jump up here. And it's diagonal from here to here. And then somewhere else, it'll drop down and it'll be like a parabola. Okay, so these are examples of a piecewise function. They are pieces of a function or pieces of different functions that are just on one graph. Okay, if you think about sales, for example, let's think about the sale price of a particular item. This particular item may be pretty consistent throughout the year, but then at the holidays, they automatically mark up the price and it gets higher and higher until the end of that season, and then it may drop back down. Okay, that's just an example of what maybe a piecewise function might look like in real world. Either way, let's go ahead and start manipulating. So it says to evaluate the function when x equals -1 and x equals 0. So for us, what that means is we need to focus on the constraints of the function. So this function, the top function, has a constraint of x being less than 0. So if your x is less than 0, you can use the top function. The bottom function says if x is greater than or equal to 0, then please use this function. So for us, x being -1, it happens to be less than 0. So we're going to use the top function to evaluate that. So when we rewrite it, we would say f of -1 equals -1 squared plus 1. We are evaluating for that piece of the function. We do not put it into both because it does not satisfy both constraints. So it's only in the top one. -1 squared is +1, and 1 plus 1 is 2. So f of -1 for this piecewise function is 2. The second one says evaluate the function when x is 0. Well, in this case, it's going to satisfy the second constraint because it says x is greater than or equal to 0. So for us to do f of 0, we're going to focus only on the second function. So we're going to substitute 0 into the second function only. So that's going to be 0 minus 1. Well, we know 0 minus 1 is -1. And so f of 0 for this piecewise function is -1. All right, so we need to evaluate when x is 2 for that previous piecewise function. So I'm just going to rewrite what the piecewise function was. It says f of x equals x squared plus 1 when x is less than 0, and x minus 1 when x is greater than or equal to 0. So for us, which constraint does it match? When x is equal to 2, is it going to be less than 0 or is it going to be greater than or equal to 0? I hope you figured it out that it is the second one, when it's greater than or equal to 0. So if I want to find f of 2, that would be 2 minus 1. 2 minus 1 is 1. So f of 2 is 1. Remember, we do not substitute into both functions, just the function that matches the constraints of the piecewise function. All right, so the domain of a function. So the domain of a function is a set of all values of the independent variable for which the function is defined. So in general, the domain excludes values that will cause division by 0 or result in the even root of a negative number. Those specific cases we'll talk about in just a moment. But we do need to remember them. So if you're taking notes, I would write that down. So in general, the domain excludes, which means it does not include, right? So it excludes values that would cause division by 0, which would make it undefined. If you divide by 0, it's undefined. Or would result in the even root of a negative number. All right, so let's take a look at that. So we need to find the domain of each function. So the first set, we have simply just ordered pairs. And so we would just list the domain of those ordered pairs. So our domain for this one remember, domain is your input or your x. So we just list all the x values that we have. It's nice if it's in order from least to greatest or greatest to least in some sort of order, not that they're all over the place, but in this case, they're already in order for us, so that's great. So I'm just going to list them. So we have -3, -1, 0, 2, and 4. And that's it. For our second function, g of x equals -3x squared plus 4x plus 5, that's one that I would suggest taking a look at in a graphing calculator. But again, if you remember just certain properties of functions based off of the way that they look from algebra 2, you'll remember that if it's x squared, if it's an x squared, that it's a parabola. Also, if it's negative, it's going to open downward. So just as a general sketch, this isn't accurate or anything, but I'm just drawing it. As a general sketch, if we know from looking at a graph that domain marks how far left and right a graph goes, or how far left and right a graph extends, knowing that I see arrows at the end of my graph, that means it's going to go further and further this way, further and further this way. What that means for us is that our domain for this problem is all real numbers. And a better way of saying it is x such that x is all real numbers. That's set notation, just a reminder. But anyways, x is all real numbers because it will infinitely continue left and right, stretching out farther and farther as we get, again, further and further down here. It technically goes further and further left and right. The last function, h of x equals 1 over x plus 5. So as a reminder, we could either graph it or we could just know what it does algebraically. Sorry for yawning. As a graph, if you remember from algebra 2, this is a rational functions. Rational functions typically look like 1 over x. Okay. Anywho, rational functions typically throw this shape. Okay, and because it says plus 5, then what I know to be true about this function is that it has shifted 5 to the left. So over at -5, it has shifted to where now that's almost like the center. And it has a vertical asymptote there. Now, graphically, it's pretty easy to see that if I were an x value and I'm writing on a function, that it is writing from left to right. It's coming from -infinity, but all of a sudden when it gets to -5, it drops off the face of the earth. It comes back and then continues on to positive infinity. So for me, what that tells me is that, well, it's all real numbers, but where it drops off at is my exclusion. Another way we can think about it is from the definition that was given a moment ago that said that the domain excludes values that would cause division by 0. Well, what could force this to be division by 0 is if the denominator actually ended up being equal to 0. So what would make the denominator equal to 0 Well, what would make the denominator equal to 0 is if this x value ever happened to be -5. Why? Because -5 plus 5 would be 0, and that would cause the function to be undefined in this area, which is what we just stated by looking at the graph here. So, in the end, what we would say for this function is that our domain, and again, if I use set notation, it's x such that x is all real numbers except x equal to -5. And that's it for that one. Let's keep going. All right, our last tries for this presentation. Sorry, I couldn't get that out. All right, we're going to do the volume of a sphere. Just in general, this is more like a logic one versus actually doing any work, but it says volume equals 4/3 pi r cubed. R is what is manipulated, right? The radius can increase or decrease. That's the movable or changeable item. So that's the dependent, that's the independent variable. Whereas volume depends on what the radius is. So V volume is the dependent variable. Either way, what they're saying is, well, based on the domain, which is R, what are our constraints? Can it be all real numbers, or is it only a certain set of numbers? If you think about a sphere, and I'm not going to be able to draw very well, it's almost going to kind of look like circumference, but just go with it. Here's my radius, right? I can get larger. Here's my radius. What type of radius can I not have? Even as I get larger than that, what kind of radius can I not have? Hopefully you could say that, well, it can get larger, so it can be infinitely large, but what it cannot do is be a negative number. In fact, it cannot even be 0. If I had a radius of 0, it wouldn't exist. So with that being said, our domain is R such that R is greater than 0. So the radius can be any value as long as it's greater than 0, so that it will maintain the shape of a sphere. That's it. On our next function, it says k of x equals the square root of 4 minus 3x. In this case, because we only see the square root of 4 minus 3x and it does not say plus or minus the square root of 4 minus 3x, what we will assume is that it's only the positive version of this function or of this radical. So with that being said, the radicand must be positive or 0. Again, just as a quick sketch why, it has to be positive or greater than 0, because positive radical functions typically sit on the upper half, right? If it were negative, it would come down here, and so then we could take all of them, but still being greater than 0. But we're not talking about the blue one, we're talking about the green line. So in order for the radicand then to be greater than or equal to 0, we'll just make an inequality out of it to figure out what the actual domain should be. So 4 minus 3x is greater than or equal to 0. I'm going to solve for x now because that, again, will be our domain. So subtract 4. I have negative 3x is greater than or equal to negative 4. If I divide by negative 3, just a reminder, when you divide by a negative and you have an inequality, it flips the sign. So really I have x is less than or equal to 4/3. So our domain, just switching colors so it could be better seen. Our domain is x such that x is less than or equal to 4/3. All right, and that is it for this section. This is 1.1 part 1 of the functions section. If you guys have any questions, please don't hesitate to come see me for tutoring.